Here's another way to look at type 1 and type 2 errors. The table kind of helps show us how everything squares up. My son just walked by and Lincoln said, "Hey, why does that math symbol look like a smiley face?" I said, "Well, it is a smiley face." That's what we want. When the null hypothesis is false, we want to reject the null hypothesis. Get out of here. On for something that's correct. On to the alternative. When the null hypothesis is true, we want to fail to reject the null hypothesis. It's true. We don't want to refute that. So that is also good. So if we are in these two squares of this matrix, then things are good. Life's okay. It's what happens when we go off this beaten path that things are a little bit weird. For example, if the null hypothesis is true and we mistakenly reject that, we've made an error. Now, the probability of mistakenly rejecting a true hypothesis matches exactly with that of alpha. So if our threshold is that 5%, you show me something that happens less than 5% and I will disbelieve the null hypothesis. Well, if we randomly happen to get that 5%, then we're creating a type 1 error if indeed the null is true. So if I happen to roll the 1 on the 20-sided dice, that's that 5% zone. It happens randomly sometimes. Then we may mistakenly reject a true null hypothesis. The probability, that's alpha. That's that 5%. If your alpha is bigger, then the probability of a type 1 is bigger. If your alpha is smaller, say if it was 1%, your probability of a type 1 error is even smaller. A type 2 error is quite a complex calculation. We're looking at overlapping normal distributions. It's in your textbook if you're wanting to go into it. It's not going to show up on the AP test. You will never have to calculate beta. But what we are going to do is wrap our heads around what beta is. Beta, the probability of a type 2 error. The probability of not rejecting a false null hypothesis. Okay. Now, a type 2 error is directly linked to this idea, this concept we call power. Power is what we're after when we are putting together a hypothesis test. More power is more better. Probability the test rejects the null hypothesis if the alternative is true. We want to reject a null hypothesis if indeed the alternative is true. If the plants grow better when listening to rock music, we want to reject the null hypothesis that they grow the same. We want to show the alternative is true. And the more power, the more likelihood of that happening. Power can be calculated by 1 minus beta. We're not going to have you calculate power per se, but we are going to be interested in ways to increase the power, therefore increase the likelihood of correctly rejecting a null hypothesis. There's a couple different ways to do this. Way number 1 is to increase alpha. If we make our alpha bigger, then we are going to reduce beta. And reducing beta increases the power, right? If we shift our emphasis over to making a type 1 error, the probability of making a type 2 error goes down. Another way we can do this is to compare alternatives further from the null hypothesis. So when my alternative is further from the null, then it becomes easier to see that there's a difference there. This one, in practice, is pretty impossible to do. Additionally, we could increase the sample size. More in your sample means the probability of you coming to the correct conclusion is higher, which is an increase in power. I'll put it down, though it's not very realistic. The last way to increase the power is to decrease the standard deviation. For some way, if we can get more consistent results from our surveys, then that is going to increase the probability that we come to the correct conclusion about our null hypothesis. So the big ones here, the two things that you can actually do in practice is increase your sample size. That's probably number one. And number two, increase your significance level. So be a little bit more willing to make a type 1 error.